We're so excited to have you here. We want to welcome you to Intro to Data Science, Machine Learning Behind Instagram and TikTok Filters. My name is Catherine Sommerfeld. I'm the Marketing Campaigns Director here at Flatiron School. Part of my team's job is hosting free introductory workshops like this evening's event to give you the opportunity to meet some of our instructors and get more of a feel of the Flatiron School experience. Corey Mickelson, our marketing events coordinator, also hosts a series of Tech in 20, where we take 20 minutes to discuss hot topics within the tech industry. A quick reminder, we'll be using the chat button as our main source of communication. So again, make sure to set that little blue button from panelists and host to everyone so we can all chat together. Without further ado, I'd like to introduce our host for the evening, Erin Hoffman. She's one of our lead data science instructors. Take it away, Erin.
All right, thank you, Catherine. So I am on the curriculum side. So I mostly spend time writing data science curriculum, but I'm kind of the resident substitute teacher for across the different data science cohorts. So this is one of my favorite lecture topics, although we've turned it a little bit more into a workshop with a little bit less math and a little bit more of like the fun stuff, I think. So this is all up on GitHub. It's available at the link shown here. I would encourage you to just sort of watch along as we go through it, and then you can open up the code later if you want to play around with it, make it your own. There is a Binder Hub link linked in the README on GitHub. So that means it can open up a container environment so that you can actually like run Python code directly in a browser without installing anything. What I'm using to show this, however, is additional software on top of it that makes it look like a slide deck instead of a regular notebook. That won't be available in the Binder version, and it'll just all appear as like a one-page thing. So just clarifying, it is the same. I'm just using an additional package to make it look like slides so we can really focus on one piece at a time. All right, let's get started. So high level, what we're talking about today. First of all, thinking about images as data. I think we all come into data science with some preconceived ideas of what kind of things we can treat as data. And so I just want to get started with explaining. I'm talking about these image filters. So what does it actually mean to use images as our data source? Then getting into a bit of machine learning taxonomy. So there are lots of kinds of machine learning, the actual like algorithms. You may have heard of things like linear regression or random forest, as well as this higher level taxonomy that is like the different types of machine learning that have different applications. So giving some examples of these filters that are in different categories within machine learning. Then specifically talking about one particular unsupervised machine learning algorithm, which is called k-means clustering. Going through a little bit of the math, not a ton of the math, and then getting into, okay, how can we use Python libraries to actually use this machine learning algorithm to make our own kind of filter, although it's completely written in Python code. So, images as data. These are some results that I got when I searched Wikimedia Commons for data, and I think this is aligning with what most people would think. So we're thinking of spreadsheets, rows of numbers, columns of numbers. On the right is some kind of like stock numbers that we're seeing, as well as graphs of them. That certainly is data. I'm not going to tell you that this is not data. But the thing that this is specifically is tabular data. So data that's arranged in rows and columns. Often those things are numbers in the rows and columns. They also could be text values in the rows and columns and still be considered tabular. But that's not the only kind of data. Just showing here an example of the tabular data that we can interact with in Python. So a CSV is a comma separated values, one of the formats that we can use to encode tabular data. So I can run this. And so all I'm doing here is I'm opening the file, I'm reading every line in the file, and I'm printing it out. So pretty simple. We can see here that, okay, we have numbers, we have commas, we can kind of just like see the data right away without doing anything that's advanced, anything outside of just what's built into Python. So those open and print, those are built-in functions in Python. We didn't even have to use a library. Another thing that we'll do pretty often is use a library to work with this kind of data. So this is pandas. It's really popular data for library for using tabular data like this. And you see here, it kind of gets displayed as rows and columns, getting a little bit closer to that spreadsheet representation. And you can also use pandas for all kinds of things, filtering, grouping, selecting certain rows or certain columns. Very powerful tool. We're not really talking about pandas today, though. What we're talking about is image data. So sort of under the hood, when you're thinking about these data files, underneath, all of it is actually being stored in binary on hard disk. So this is just an image showing a bunch of binary numbers. I don't actually know what this is supposed to be underneath, but just a stock image of binary data. But in general, every bit is a 1 or a 0. And then we have these bytes that are these groups of 8 bits. And you see they're all kind of arranged like this to represent some other kind of data that's stored on disk. Usually a 1 or a 0, it doesn't really mean 1, it doesn't really mean 0. It's being read by the software to mean something more in depth. So if we check out our image data, so again, here I'm doing very similar code as I did with our tabular CSV data. I'm opening it and then I'm printing every line of it. There's a slight distinction that I've added this RB part, which means that I'm reading it as bytes, like I mentioned, the category of the little separation that we saw in that binary data visualization. And this is what an image looks like. So this is a JPEG image. There's some kind of weird stuff in here. I really don't actually know fully the like dollar signs that we're seeing in here. That's something to do with the image format. But at a high level, what I mean to point out here is, so there's this \x and then FF or D8, FF, E0. Those actually are those binary numbers, like we kind of saw in that visualization. So this, like, we're taking FF as an example here. And like this is really what it would look like in binary, is all ones. Similarly, we take that like D8 and make it into a binary number. It would be this. All this is to be a data scientist, you don't need to be able to like read binary numbers, but it's just sort of conceptually, like, how do we store an image on a computer? It actually all just is sort of data under the hood. So most of the time, we're not going to try to read it directly like this to make sense of it. Instead, we're going to use Python libraries. So this is a big reason why Python is such a popular language, especially for data science, is it has so many libraries that can do so many things for you. So this PIL is short for Python Image Library. It's also sometimes called Pillow. This is where we are importing some functionality so that we can actually, instead of doing like we did up here and opening it and seeing all of this kind of binary data, this has functionality that we can assign it to a Python variable and then display it. So there's our image. It happens to be the header image from the beginning of this presentation. And it's just sort of insta-magically works. So we're going to be using some things like that where we talk about the concept and then we use Python to do a lot of work for us instead of really going through the nitty-gritty details. Just checking any questions. All right. So going beyond, okay, we know we can use images as data because just like our tabular traditional data forms, it really is just binary under the hood. We can treat the image as numbers in various different ways. So from that, let's then start thinking about machine learning. So there certainly is a form of data science that is not machine learning. So you can be doing things with statistics, doing like A/B testing. A lot of people would consider that to be data science, but not machine learning. But the part of data science that we're talking about today is machine learning specifically. And we're going to look at that through the examples of these filters. So one of the most key distinctions between different types of machine learning is this distinction of supervised versus unsupervised learning. Supervised machine learning is probably, if you feel like you have a definition of machine learning in mind, that's probably the kind that you're thinking about. So that means that you have some kind of labeled data and you're using the labeled data to make predictions about some data that doesn't have labels. So that could just be some kind of unknown. It's often used for like projecting into the future, where like we don't know this because it hasn't happened yet, kind of unlabeled data. Or it could just be we have people label some fraction of our data set, and then rather than having people waste their time on labeling the rest, we train a model to do it instead. So that's supervised machine learning. And unsupervised machine learning is less well known. What it means is learning patterns from the data without these labels. So there still are some assumptions that we make going in, and we'll talk specifically about the K and K-means clustering. We're kind of assuming that that is an appropriate way to learn from the data. But in general, we're saying, I, as the data scientist, don't actually know what I'm looking for. I want you, the machine learning model, to tell me what you see here. And so the main types of unsupervised ML are clustering, dimensionality reduction, and anomaly detection. And specifically, we're focusing on clustering today. So these are a couple examples of supervised ML filters. I did want to add a clarification in here. These platforms seem like they're trending towards using the term effects and filters as like different things, but I think colloquially people usually call these filters, even though formally they're effects within the apps. But these are examples of filters that we know must be using supervised ML. So the one on the left, putting sunglasses on the guy's face, and the one on the right might be a little bit harder to tell what I'm looking at here, but specifically I'm talking about this background, which is the green screen effect on TikTok. So I'm just going to pause for a second. Can you think of what label is it looking for in each of these filters? Go ahead and breeze on through, tell you the answer now, which is on the left, it's looking for a face so that it can position the sunglasses specifically over the eyes. Like you would say that this filter is not working properly. If it just puts sunglasses somewhere, that's not the expected behavior. If it puts sunglasses on your chin, that's also not working properly. So in order to make a filter like this work, you had to have a bunch of people label, okay, this is a face and these are the eyes. Here's a face, these are the eyes. So that when this camera is pointed at a person, it can say, okay, we've detected a face and we're going to put the sunglasses in this spot. The other one is pretty similar in that it's looking at facial detection. We have a lot of things related to faces with cameras because people like to take pictures of themselves and of other people. But what it's doing there is it's detecting the background. And so we also see that in Zoom backgrounds, lots of things where they're trying to detect, looking at an image, what part is the background and what part is the foreground. And that again, you train that on getting a ton of labeled data where someone went in and they said, okay, this part should count as background, this part shouldn't. And then eventually you can get a model that performs really well at this compared to a simpler rule-based system that really is just like making assumptions. You could actually have a model that has learned from past data. But then, okay, what about unsupervised ML filters? As I've said, we're not getting into supervised machine learning today. Not that it's impossibly complex for an intro workshop like this, but it is like, there is just a lot to it. So what we're focusing on today actually is the unsupervised ML filters. And so what this is doing is it's both of these filters actually in different ways. One on the left being an Instagram filter. The one on the right is, I believe, for like a Facebook camera. So more like a Facebook stories filter. So what these are doing is they're looking at the image, finding the colors in the image, and then doing something with that information. So the filters on the left are doing more of adjusting the saturation, the brightness, things like that, based on the colors that they find in the image. The one on the right, which is actually more like what we're going to be doing today, is it's just finding colors in the image and then making this little set of rectangles that have the colors just as a fun effect. So I want to pause, clarify here. I'm not teaching you how to make Instagram filters. That is much more of a design skill set. These are the links. If you are like, no, what I actually want to do is design filters where essentially those filters are all built on top of machine learning, but you don't have to train the filter on like, this is what an eye is. They kind of have built in like, oh, okay, you're looking for the eyes in your augmented reality design. So those are the links. Again, feel free to check them out after the workshop. But what I'm talking about is really the algorithm, the math that's underneath, and not just the like, how do you actually make these things? So specifically, that one is called k-means clustering. So just wanted to recap lots of data science basics that we just flew by very quickly. So images are kind of data. Data science is not just limited to that spreadsheet style tabular data. Python code can be used to interact with data, and especially we can use Python libraries to make our work easier. So just thinking of that like binary code version of the JPEG versus the Python image library version of the JPEG, you can see immediately that libraries can do so much work for us. And then getting more into the conceptual side, machine learning includes both supervised ML and unsupervised ML, and that these kind of filters use both kinds of ML. And in this session, we're specifically covering k-means clustering, which is an unsupervised ML algorithm that can be used to make a color palette filter. So our color palette effect is what we're going to be making. So k-means clustering. So clustering, as I said, is one of the main types of unsupervised machine learning. This is an image from scikit-learn that I think does a great job of showing just all the different ways that data could be arranged and the ways that the different clustering algorithms would attempt to make it into clusters. So I mentioned assumptions previously. If you look across that very bottom row here, I think we can all intuitively realize that data is not well suited for clustering. Like, at least in the 2 dimensions that are being plotted here, there aren't really clusters. Like there just is uniformly distributed data. So one of the maybe issues with clustering as an approach is if your data doesn't actually have clusters in it, if it's uniformly distributed like this, then clustering, it'll still give you clusters. Like you see here, all of these different algorithms are trying to find clusters in it, but are not doing very well. Whereas data like this second from the bottom row, that's really obviously well suited to clustering. There are these just like, we say clusters, groups. You can see they're like these tight little groups that there's this distance between each of them and not a lot of spread within them. So that kind of data, very appropriate to use clustering on. And then these top rows are more complicated, and it really depends on the clustering algorithm that you're using, whether it's going to get it right. So like, especially these like kind of funky clusters where they're concentric. So one is in the middle. So you really have to be thinking not just X and Y, but like radially in a circle. Only some algorithms are going to know what to do with that, versus k-means, which is what we'll be using. You can kind of see does great on something that's obvious clusters. I think this is pretty good on these sort of mixture of clusters. So there's some overlap and different amounts of spread in each cluster. So definitely more challenging. It does pretty well. Here, not so great because it's kind of like, it's not really a circle, it's in a line format. And then these top ones, definitely not so great. So, but as high level, this is what we're trying to do, is trying to find what are the groupings within some data. And that you, as a data scientist, you don't know what groups the different data points should be located in. And that's why you're running a clustering algorithm. So pivoting slightly away for a minute from our TikTok, Instagram filter example to something that's a little more two-dimensional, easier to grasp. The classic use case for clustering is market segmentation. So this idea of you have customers, but they don't all behave the same way. And in particular, maybe some of them respond really well to getting coupons sent in the mail. Maybe some of them respond better to coupons sent by email. Some of them don't want to receive any marketing materials at all, something like that. If you want to start figuring out, okay, at least what are the patterns? So once I know what the groups are, I can dig in and try to find out more about them. That's a use case of market segmentation. So you're first asking the algorithm, find the groups, and then you would go in with your domain knowledge to figure out, okay, what do we do now that we know these groups? So this is just a made up example here of average purchase versus time since last purchase. And we have about 4 clusters here. We can kind of just see intuitively of about 1, 2, 3, 4 clusters in the data. And so then this is a little animation showing the k-means algorithm applied to those clusters. So it's starting out on different sides, but each time we're effectively doing the same process, which is, it's a little tiny, it's like a lime green dot in there, which is a centroid. There are a couple different definitions of centroid in math, but centroid is the center of a cluster in this context. And so it starts somewhere. Then you calculate for each data point, so that is the black, what is the nearest cluster? So you assign that data point to that cluster. Then you calculate the mean of the things in the newly created cluster, and you move the centroid to that mean. So we kind of saw the animation of the centroids moving and those red lines changing as they minimized the different distances. And so then one thing that I also want to introduce here is that this is an optimization kind of algorithm. So there is something that we are trying to minimize in the math behind this. And what we're specifically trying to minimize is for each of those centroids, we're trying to make the distance between each point and that centroid as small as possible. And so you'll notice here, all 4 of these examples, they had 4 centroids. And the number of centroids is the k in k-means. So they're always going to have the number of centroids that you specify as the data scientist. And you will notice also there is some randomness or some indeterminate behavior, because these clusters, they're not like those like really tidy, really separate clusters that we saw. This is more like what you see in real world data, is messiness and overlap. So we're getting different clusters each time. And that's just the nature of a k-means algorithm. It is something that we are going to try to control for in our code using a random seed, so that the centroids start out at the same place every time. But I do want to emphasize here, it's an analysis technique. It's not a technique that finds like deep ultimate truth in your data. But I think looking at each of these clusters, we can kind of see, okay, like I see where that came from, even though we might look at them and say, oh, I think this cluster is better, is what I would have drawn. But usually in reality, this is nice 2-dimensional projection. In reality, you'll be doing something much higher dimensional, where you can't just go in and draw the clusters, because if you can just go in and draw them, then why are you using an algorithm to find them? And in our image data, we're going to go ahead and use red, green, blue as our 3 dimensions. So we're already getting to the point where we can't plot it on a regular XY axis like this. And that's why instead we'll be using the algorithm. So not a ton of math here, but I do just want to show a little bit of this is how you would encounter this material. In a data science context is, so what are we trying to minimize? The name for it is inertia. Again, we're borrowing words from physics. Data science loves to just borrow, words, Greek letters, all kinds of things from different math and physics fields. We're taking mu, the mean, it's a pretty typical math notation. And what we're just saying is, for all the clusters, for all the points in the clusters, we're trying to minimize the difference between each point and the mean or centroid of that cluster. We're using squared differences. That's a relatively common thing here. In data science, part of that just is that some forms of difference. So like if we took this and we literally just took it as the value minus another value, that could give you something negative. And we're usually saying, no, I don't care if we were wrong in one direction or another direction. We were just off. So like, we don't care if it's a really far X direction or minus X, like we don't care. And so that's why we tend to use squares. It also tends to help with some of the underlying math, that a squared term tends to be more differentiable. And then also this like bar on either side, that is a stand-in for distance. So in a 2-dimensional really no, in a one-dimensional space, we could just say like one minus another if these were just a number line rather than even something two-dimensional. But this is a stand-in for other kinds of distance. So we're mostly going to look at a Euclidean distance. So that is like your a squared plus b squared equals c squared kind of distance. So the algorithm then to try to minimize this inertia is we initialize some centroids, so k of them, and their means are set somewhere. There are actually a couple different variants of this algorithm that specify different ways for it to start. Kind of saw with those GIFs earlier how they started like top, bottom, right, left. Usually we would do something a little more intentional than that. Maybe fully randomly distributed, or maybe actually do some pre-processing of the data to make better guesses of where our first ones would be. So those are different forms of initialization within the same algorithm. Then once we have those centroids, we are finding the nearest centroid for each point. So this like argmin notation with J, that just means for every X value, so for every data point with however many dimensions, we're trying to find the centroid that is nearest to it. Now that we have our clusters assigned, we actually then shift the centroids to a new place. So we assign a new mean. And then we repeat steps B and C until the centroids are no longer moving more than some threshold. You can kind of imagine like the way you kind of saw those things moving and they slowed down. You could maybe, if there's not one perfect solution here, you could maybe like infinitely try to optimize this. But that's something where most optimization algorithms are going to have stopping criteria so that they don't run forever. They run until they've found an answer that is good enough. So here we don't repeat the like randomly assigning centroids, but we do keep on repeating, assigning the points and moving them until that movement is small enough that we stop and we say, okay, cool, we're done. We've found sufficiently good clusters. So now that we have our clustering algorithm, how is this relating back to Instagram, TikTok filters? So how can we apply this technique to images? And then showing, again, images as data, and then using that data then to actually annotate back onto our image using the result of our modeling. So here I previewed this a little bit already, which is that, okay, now we're not talking about this like just values X that could have as many dimensions as possible. We're specifically going to think about our images as being red, green, blue. So thinking of them as pixels, where each pixel has a red, a green, and a blue value associated with it. And so this kind of approach to images, I just wanted to include these examples. This is not exactly what we're doing, but the idea here is you can reduce the palette of an image to save the amount of space. Like I think if you look at the image on the right, those sort of JPEG artifacts are might be familiar for an image that has been shared and edited a lot of times on the internet. That what we're trying to do is find colors that are close to each other. And this is the way that we're defining it. So we're defining it as this Euclidean distance. So the squared differences between the reds, the greens, the blues, and then take the square root of all of those things. So that's the same approach used for this quantization that's pictured here. But what we're going to do is reduce it to even fewer colors. Then this is saying like, okay, we have enough colors to reproduce the whole image. I don't actually need enough to reproduce the whole image. I just want to make a little color palette layer on top of the image. So I've gone through conceptually what is the algorithm and like some of the math formulas under it. So using just Python itself, I would say maybe once we loaded in the image using Python image library, we could use things, lists, dictionaries, and maybe the math built-in module of Python, and like we could code all of this out. But instead, we're going to use scikit-learn. This is a really common pattern in data science is you kind of learn the conceptual. It's important to understand the conceptual before you just dive into using the library, because you won't be able to understand your results or do any real troubleshooting if you don't understand the conceptual part. But the code tends to be much simpler for data science applications than a lot of software engineering applications. So here, we're just importing a k-means model from a library called scikit-learn. Scikit-learn has many, many different machine learning algorithms. So unsupervised ones like demoing here, but lots of supervised algorithms also. And they really all have just the same interface of you import it and you feed the data in, and then you get your results out of it. So it's pretty cool. So specifically for this example, I'll use this image from the Gallery of Fashion. I just wanted something relatively simple. And then we'll get into applying the same algorithm to several photos also of things with more depth and more colors, things like that. But I just kind of liked the aesthetic of this. It's from the 1800s fashion plates. So same as before, gonna go ahead and open it up with image library, and then we can use the display function. Again, it looks pretty much like we expect. Now let's actually fit the model on it. So we're going to need another library here. So this is NumPy for numerical Python. And this is just changing the format of the data a little bit. So this image.getData is returning data in a format that's better suited for the image library. And we want it to be in a slightly different format that's better for scikit-learn. So we just call np.array and pass in that image data, and then pixels. So this is just echoing out because I'm in a notebook environment, showing what's in here. So this is an array, and we can kind of see out here one level of depth, and then inside of each we have a nested array and 3 values inside of that. And those are the RGB values out of 255 is the way that they're represented by this library. And so this is a nice little feature of the notebook interface. There are many, many more pixels. Don't worry, there's not just 6 pixels in this library, but this is just a preview of what we'll see in here. And so let's see. I see a couple of people asking about the slide deck and recording. So yeah, so I can send out in the chat. There is the notebook with a link to open it in Binder, and just like the source code in GitHub. So yeah, the fact that it looks like a slide deck, it's actually a library on top of a Jupyter notebook. So it won't look like a slide deck for you. It'll look like a Jupyter notebook. So continuing on here, we have our image as data as an array of arrays of numbers. And here I'm specifying k equals 6. Again, this is sort of like an assumption. I can tell you it's because I've looked at this image before and I've tried a couple of different k values, and this is the one that I think looks nice. That's where the k came from. It is something that you kind of have to choose based on what you've seen in the data. So I'm choosing 6. We're going to find 6 clusters in this image. And so all we're doing is using that k-means model that we imported and fitting it on the pixel data. Go ahead and run this. It's a little bit slow. I expect it. Okay, ran faster than usual. All right, we're doing well. Sometimes that takes like a minute or two to run. And so then, like I mentioned before, inertia is the measure of how well k-means performed. It was the thing that was trying to be minimized. That's our inertia. I wouldn't worry too much in general about what does this value mean. You can generally imagine that the more clusters that you add, the lower the inertia will get, because there's just, you can have a cluster closer to each data point. If you had a cluster, if you had one for each data point, then you would have an inertia of 0, but you also wouldn't have a useful cluster. So there's a plot called an elbow plot that you can use to really find like what's the best value of k for your data. I'm mostly just sticking this in here to show you like what I was talking about with connecting the concept to the model that we're using, that it's all interrelated, but usually we can use our libraries to do most of the work for us. So then there's our centroids. They're encoded as cluster centers by this library. And so here they are. They are, again, it's this double array. And then inside each one are 3 numbers. They're not the same numbers as up here. They're actually these kind of weird rounded values that like don't actually work as RGB values, because normally an RGB value needs to be exactly an integer. But as you'll see later, we're actually going to rescale these so that you can, they'll all be values between 0 and 1 later. So we don't have to worry about the fact that these aren't really valid RGB values. And yes, elbow plot is the type that helps you determine the best value for k. There isn't always like a single right answer. You're just always trading off having a lower score versus having a meaningful number of clusters. So now, okay, we found those RGB values. What do they actually look like? Because this is very visual. We don't want to just see the numbers. So I'm going to introduce yet another library. We use a lot of libraries. This one is called matplotlib. So it's a math plotting library. And so first, actually, I'm going to show what does it look like if I just show our original image using matplotlib. Pretty similar. It ended up getting scaled a little bit smaller. And there's also X and Y axes on it, which we'll take away later because that looks a little bit silly. But just starting with that, then, okay, what are our colors? What did we actually find? And again, here I'm scaling by 255. So we actually don't need to worry about the fact that those weren't valid RGB values. This is a really nice thing about NumPy. So color, we're looping over here those cluster centers. That still means color is an array. And yet we're able to just divide it by 255 instead of having to loop over and divide each of the elements in the array by 255, because NumPy has something called broadcasting. which actually allows you to apply the same math operation to everything in an array just all at once with this really simple syntax. So that is how we did that. And here are our color swatches that we found. And so then the final step is, okay, how do we combine them together? We have our image, we have our swatches. This is the code for that. So we need one more thing, which is a rectangle from Matplotlib in order to draw on an image. You see here, these are just like the entire graph is that color was the hack that I did. But we'll do this a little bit more properly here using the rectangle. This is the same code as before, setting up the plot and putting the image on it. This stuff is really what I ended up sketching, like literally sketching on paper to make a grid that I thought looked nice. So really just thinking of something that will scale regardless of the K that is selected, to put a nice amount of boxes that are farther to the right. And so this, I ended up making a grid that is like 34 by 6 for something that had 6K. So that's where this came from. This is not related to the math of the k-means. It's just what I happened to come up with to make something that looks nice. Fairly similar logic here to some like HTML, CSS type figuring out how to lay out elements on a page. But then here we're looping over those cluster centers. Again, we're establishing an anchor point for a rectangle to be drawn, and we are drawing it again using NumPy broadcasting to scale that down from 0 to 1 instead of 0 to 255. And also I put a white border around it because that's what the example did. And finally, I hid the axes labels just because those don't look so nice. And there it is. We've got our color swatches or color palette on top of the image. So that's really fully end-to-end here. We've loaded the image, used k-means clustering to find the clusters of images, then plotted them using Matplotlib. That sort of workflow of having lots of individual cells in a notebook is good for exploring, good for explaining, but really you then would want to make this into a function so that it can be reused instead of having to like go through, if we want to use a different image or a different K, that's what this does. So it parameterizes what image and what K, and then really just repeats that same logic through. So loading the image, fitting the model, setting up a plot and putting the image on it, setting up the layout grid, and plotting a rectangle for each of the clusters we found, and again hiding the axes because we don't like seeing those axes. And so running that didn't do anything because I was just declaring the function. But now I can do, so here's the same image. Before we were doing 6, now we can do 4. These I do expect to take kind of a while to run. So I'm gonna load them and start them running before the last one is done probably. But so here we're seeing 4 rectangles instead of 6. This one I'm taking again the same image and I ask you to find 10. I do think the 10 looks pretty nice here. It's a little slower, but just a fun variation there. And here we have a couple more actual photos where I'm doing 4 color swatches. So photos versus this that's more of an illustration. So long as it is a raster image. So something like an SVG where it's a vector image wouldn't work with this approach. But so long as the image is stored in pixels, it can be an illustration or it can be a photo, and they both work. So here's just some sort of different toned workstation stock photos I found. This one is fun little neon example. This one, someone painted an orange blue. We wait for that to load. So I don't really know why someone made this photo, but I thought that was a fun use case for this filter. And then this is our last one in here, which is just another photo. So that is it. These are some credits for the images, and also a computer science educator, Kate Compton, was my inspiration for some of the ideas in here. But yeah, that is k-means clustering and how it can apply to build something like an Instagram or TikTok filter. All right, thank you. And I see I have a question in the chat. Say, Catherine, definitely let me know if there's a more formal process that we want to use. But I'll just go through these questions in order. So what are the most common tools, libraries for data scientists day to day? Pandas, RStudio, etc. Yes, so I think it depends on the individual, and it depends on the organization, whether they're more of a Python place or more of an R place. R is really focused on statistical tooling. So statistical testing and inference is really important in the R community. So they tend to have more libraries that can do more sophisticated things related to that. Pandas, very common for data scientists. I would say, other than Python's language, pandas is like the single most common thing that we hear our students are using in the workplace. And then it really depends on the data scientist, whether they're using something like scikit-learn, whether they're using their specialized big data tools. So that is like Spark or PySpark. Then there is deep learning, which we didn't really talk about at all. So those are much more computationally intensive and generally more accurate models, so like neural network. So that would be a library like TensorFlow or PyTorch. How do those which Disney, Marvel, singer, celebrity face matches work? Are they supervised learning, and do they use k-means? I'm pretty sure those are random. So that is something interesting. More commenting here is like a social scientist observing people than a data scientist, but people like to pretend that machine learning was involved with these filters, and sometimes it's not. So maybe still like finding the face, so the one that's like half your face is replaced by a celebrity. That's certainly using supervised learning to find where the face should go. But as far as actually finding a match, I'm pretty sure those are fully random. And in general, k-means clustering is more related to color in these kind of filters. So I don't think that those filters would probably use this particular algorithm. And then, yeah, how time efficient are the algorithms? It seemed to return answers quickly. I would say, yeah, they were faster than I expected this time. They depend on the variance, like the spread of the data. So you don't really know how quickly the model is going to run until you run it. You do know the more data points there are, it's going to be slower, because every single iteration, it is finding all of those distances between the centroids and all the data points. So you could imagine if I had an image that was like a really high definition image compared to these, which are generally, I think they're around like 500 pixel wide images. If I had something really, really HD, the same algorithm, even though it's finding the same number of points, same number of centroids, if there's way more pixels involved, then it will be a lot slower. And then last one in there, it seems that the job of a data scientist is to understand the concepts, then applying the right algorithms and models from the library tools. Yeah, I'd say that's correct. And also just knowing what tools are out there and how easy or difficult they are to implement. So if you know, oh, I could use k-means for this, scikit-learn has k-means built in. So all that means is I just import the model, put in the data. You might have to do some processing before you can put the data in. But then you're done. Versus if you see some clustering algorithm in like an academic paper that's really just written in math equations right now, and you would have to fully translate that, you would be able to use something like NumPy to make it a little bit easier than just like having to write like looping over something to find the sum. NumPy is great for like, you can just say dot sum or dot mean, and it will just give you that value back instead of you having to write a loop. But yeah, that would be way slower. So just having an awareness of the toolkit so that you can talk to your stakeholders to understand this is a problem that's solvable. Also, you always have to communicate that uncertainty that like something can be theoretically solvable, but it might turn out that the data is like that bottom row that I showed on the clustering, that actually there aren't clusters here, sorry. Like we can apply a clustering algorithm, but if there aren't underlying patterns in the data, it just won't work. But once the stakeholders you're working with understand that, then yeah, applying the right algorithms and the models using these tools is the most common pattern. It's really only like research data scientists, sometimes they're just called applied scientists, who are writing algorithms themselves versus using the ones that are built into the tools. And then a question about, to what degree do you need to know math and statistics? So I will say statistics, we spend a fair amount of time teaching. So really, if you don't have any like statistics class that you've taken, that is totally fine. As long as you have like high school level math knowledge, so you understand how to read some of these math formulas, you understand certainly things like variables and functions, and then some of the basic statistics stuff, we do cover it, but we cover it super quickly. So things like a median versus a mean, or like the difference between a bar plot and a histogram, those we kind of consider to be like the high school level things where you're required to have a high school diploma for our program. And so those are considered like, maybe you forgot it, but you've learned it at some point. Again, it varies. If you want to be at the highest level of data science and like developing new algorithms and publishing them, that's usually fully a PhD in the subject, really diving deep. But to be a practitioner in data science, you don't need that level of math. And then another one here, how is data science different than data engineering? So this is something that has changed over time. It kind of used to be that using Python rather than using R made you a data engineer rather than a data scientist, because if you're writing code in Python, you can actually work in a much more software engineering style capacity. You could take like that function that I wrote there, you could deploy that function as an API, and it could work, scaled to like using cloud services, all that. That used to be more called data engineering. Industry has shifted some. So more often, data engineering is a bigger focus on just the data querying side. So doing the filtering, grouping, ordering, subsetting, transforming things, data cleaning. It often uses SQL rather than Python, but not exclusively. But yeah, that tends to be the modern definition of data engineering, is almost all SQL and just really focused on really getting data from one source into another format for someone else to use it and transforming it or combining it along the way.
Okay, if there are no other questions, we'll wrap up. Just want to give anybody time if they have anything else. Okie doke. So thank you so much, Erin, and thank you everybody who zoomed in to join us tonight. If you have further questions about Flatiron School, I am about to drop a link into the chat with a link to schedule a chat with our amazing admissions team. As a reminder, you'll receive a copy of tonight's presentation within 3 business days after the event. And if you'd like to see previous events, you can head on over to our YouTube channel and subscribe. Again, thank you everyone for joining us tonight.